So okay, so now let us again continue with this. So we have been talking about this YgD1 transformer. So I see, I see, so I see from this. So let us look at ICs IAC minus ICB, IAC minus ICB. IAC is, we said that it is IC by root 3, I capital C by root 3, and ICB we said that it is IB by root 3. So it is 1 by root 3 into I capital C minus I capital B. So if I take common, here there is one mistake, it should be Y. So it should be again Y by root 3. So IC is VC minus VC by root 3 plus VA by root 3, and minus IB, I capital B is VB minus VB by root 3 plus VC by root 3. So this is given as Y V capital C by root 3 minus V capital B by root 3, and then VA by 3, then minus minus plus plus VB by 3, and then minus VC, so twice V small c by 3. So this is equation number 6. So we have got 6 currents, 6 primary currents given by equation 1, 2, 3, and 6 secondary currents given by equation 4, 5, 6. And all these currents have been represented in terms of these 6 voltages: V capital A, V capital B, V capital C, and V small a, V small b, and V small c. So we now can simply write down these equations in the matrix form. So if I now write down these equations in a matrix form, so then therefore in the matrix form I would now like to write down. Now again please note that when we said, one thing you must remember, when we said that we would like to do a transformer, please note that here our transformer model principle was that if I have a transformer, some transformer, any connection of transformer, and this is phase A, phase B, phase C. So it is I capital A, I capital B, I capital C, these are entering the transformer, and the model which we like to seek is that at the secondary side also our current should be again entering I small a, I small b, and I small c. That's, I mean basically, I mean that is what our model which we wish to seek. And we said that, well, we will see the reason of this type of modeling when we actually discuss about the load flow analysis of rather, I mean 3-phase power system. But here So then therefore basically at the secondary side we would like to represent the currents to be entering into the transformer, whereas here in this connection we see that our currents are actually going out of the transformer. So then therefore in our model we have to take these currents to be negative, right? So then therefore our model should be, so then therefore our model is, so model, so therefore our model would be I capital A, I capital B, I capital C and minus IA, because I would like to have the currents in the negative direction, minus IB which are IC. So that would be some matrix, that would be some matrix which we will fill up. So some matrix which we will fill up, and at the secondary side it would be V capital A, V capital B, V capital C, small a, small b, small c, and is equal to, so I take y common because y is there in all the equations. So first equation I capital A from equation 1, VA minus VB VA, so it would be 1, then 0, then 0, minus VA by root 3, so minus 1 by root 3, plus VB by root 3, so this is 0 and this is 0, right? Then VB minus VB plus VC, so this is 0, 1, 0, minus VB plus VC, so it is 0, minus VB is 1 by root 3 and plus VC is 1 by root 3. IC, what is IC? It is capital C minus V small c plus VA. So capital C, so it is 0, 0, 1. Then it is minus VC plus VA. So plus VA means 1 by root 3, and then 0, this is minus 1 by root 3. Okay. So this is the primary side. So now at the secondary side, IA. Now this is IA. Now because this is IA, so then therefore I have to write down minus IA. So then it will be minus VA by root 3 plus V capital C by root 3. So minus VA by root 3 plus V capital C by root 3. So it would be minus VA by root 3 plus capital C. So minus VA by root 3, 0 plus capital C, right? And then it is plus 2 by 3 minus 1 by 3 minus 1 by 3, because I am taking minus 1. So it is plus 2 by 3 minus 1 by 3 minus 1 by 3. So that is minus IA. Minus IB would be VA minus VB. So it is VA So 1 by root 3 minus V capital B 0 0, and then it would be minus 1 by 3 plus 2 by 3 minus 1 by 3. So it is minus 1 by 3 plus 2 by 3 minus 1 by 3, right? And then the last one is V cap IC VB minus VC. So 0 0 VB. So 1 by root 3 minus VC is minus 1 by root 3, and then minus 1 by 3 minus 1 by 3 plus 2 by 3. So it is minus 1 by 3 minus 1 by 3 plus 2 by 3. So this is the matrix. So you see, so then therefore, if I now do the partition, so if I do this partition, so I have done the partition. So this is y1, this is y2, this is y3, and this is y4. So that's how this matrix would be given. And again, you can see very easily that y2 is transpose of y3 and vice versa. So these two are transposed to each other. This one is actually, I mean, still an identity matrix, but this one is not an identity matrix, right? But these two are again, I mean, these two are actually transposed to each other. So then therefore, if I now say that these vector as IABC, I capital ABC, and this vector, if I say that this is I small ABC, so I small ABC is actually minus IA minus IB minus IC, and this vector, if I say that it is VABC, and this vector, if I say that is V small ABC, so then therefore this relation can be written as I capital ABC, I small ABC is equal to y1, y2, y3, y. It is V A B C V small. So this completes the model of an YgD1 matrix, right? So now by this same process, we can do the modeling of, let's say, YgD3, YgD5 by the same process, YgD7, YgD9 and YgD11, but I am not going to do them. I mean, if you follow the same process, identically same process, you will be able to find out these four matrices y1, y2, y3 and y4 very easily. So I suggest you to derive these matrices by yourself. So it would be a real fun. So you should also have some fun. So it would be a real fun. So by this we complete the modeling of YgD1 or rather YgD matrices. So we complete the modeling of YgD matrices or rather YgD transformers. So now let us continue with the YD. So now let us now consider YD1 transformer. So how to go about that? So for YD1 transformer, so it has got no difference between YgD1 transformer, right? In this case also basically the delta side voltage lags the star side voltage by 30°. At this side also delta side voltage lags the star side voltage by 30°, or rather when we are talking about the delta side voltage we are actually talking about the phase A voltage. I mean whether it is actual phase A voltage or whether it is let us say the virtual phase A voltage, it does not matter. So essentially the phase A voltage of the delta side would be lagging the phase A voltage of the star side by 30°. The only difference is that now the star side at the primary side is not grounded, right? It is not grounded, whether in this case it was grounded. So then therefore how do I go about this modeling? So to do that I will again, so what we do is the same thing. So today we will just complete the connection and then actual derivation we will do in the next class. So we do like this, same thing, the process is basically the same. So what we did again as the same, we have taken 3 transformers, their windings, we mark the dots. The process is always the same. I am again and again repeating it just to uh, emphasize that there is no change in the basic process. So if we understand the basic process, it should be very easy. So again we mark the same points or rather same terminals A1, A2, B1, B2, capital C1, capital C2, then small a1, small a2, small b1, small b2, small c1, small c2. So we have just now taken it. So now we have to make the connection. So now here YD, so we make an Y connection. So for making an Y connection, we connect ABC together. Let's say A2, B2, C2, we have connected together, but we are, because it is not grounded, we are not grounding it. Just to emphasize, in the last case we have connected A2, B2, C2 together and we have grounded it, but here we are not grounding it, otherwise it is the same. So then therefore we call it phase A. So this is I capital A. We call it phase B, current is I capital B, and we again call it phase C, current is I capital C. So we have first taken the windings only and make the connection at the start side. Now we will do the vector diagram at the start side. So phase A, phase B, because it is star, phase C. So this is phase A. So it is A1, A2. We are just reflecting this. So between phase A. So and from phase A, this is A. So from terminal A1, I am calling phase A. And from terminal B1, so this is B1, B2. I am saying that it is phase B. And this is phase C, and it is terminal C1 and C2. So C1 and C2. So this is the connection. Please note, here we are not making the ground connection. Please note that I am emphasizing it. Here in this vector diagram, we have made the same thing, but only difference is that here we have made the ground connection. We have connected the star point to the ground because it is YgD1. But here, because it is not grounded YD, so we are not connecting this neutral point to the ground. So this completes the phasor diagram at the primary side. Now it is so now because so now this is the initial so this is the phase ABC voltage in phase, that is this is basically the phase ABC voltage which is in phase with the star side ABC voltage. But my because it is YD1, again I repeat, so my phase A voltage is here, phase A voltage is here, then my phase B voltage would be 30° from here, and my phase C voltage would be 30° from here, right. So this is my phase A voltage, this is my phase B voltage, this is my phase C voltage. But my line to line voltage, because it is star because it is delta connection, so I will actually get line to line voltage. So I will get this voltage only, I will get this voltage only, the voltages in the brown, and I will get this voltage. So these vectors which are drawn in brown, I will actually get these voltages, right. These vectors which are in solid but blue, those are the virtual ABC voltage, and this virtual ABC voltage is 30° lagging that of the star side ABC voltage because of this vector connection YD1. Now because this is, so now I say that this is phase A has to be, and this is phase B voltage, and this is phase C. So now I simply mark A1, A2, and because this is parallel to this A1, A2 and B1, so this is parallel to this B1, B2, this is parallel to this, although it so small C1, C2, right. So I again, so then therefore A2, B1 will be phase B. So A2, B1 is phase B, then B2, C1 is phase C, and C2 and C2A1, C2A1 A1 is phase A, right. So we call it I small a, it is I small b, these arrows are not necessary, so let me, so arrows are not necessary here, it will actually create confusion. So this is IC and this is phase C. So this is phase B, phase B, phase C and phase A, and this is phase C. So ABC, IA, IB, IC, and this current is IA, this current is IB, this current is IC, and with this current would be in phase. So I call it IBA, and with this current would be in phase. I call it ICB, and with this current would be in phase. I call it IAC. So this completes the vector diagram as well. So now if you compare this vector diagram with this vector diagram, there is practically no change except that at the start side there is a ground connection because it is YgD1, right. Otherwise there is absolutely no change. And if we look at this connection diagram, there is also absolutely no change except that at the star side there is a ground connection, whereas here in this case this neutral is not grounded because it is YD1. So we are talking about YD1. So that's why, although it is almost similar with this YgD1, practically same, but only difference is that as far as the connection as the vector diagram is concerned, only there is no change, only there is no ground connection anywhere in the connection or in the vector diagram. But absence of this ground connection makes the calculations much more involved, because now IA cannot be written as Y into this voltage minus this voltage. In the earlier case, because there was a ground connection, so then therefore the voltage at the primary side was VA, right, because my Vn was 0. Actually basically the voltage at the phase A of the primary side is given by Va minus Vn, but because Vn is 0, so then therefore it ultimately was Va, and of course my reflected voltage is Vba by root 3. But when here in this case, actually my voltage across phase A, for example, is actually Va minus Vn, and because this neutral point is not connected to ground, so then therefore I do not know what is the voltage of Vn, right. So then basically this voltage Vn, that is basically the neutral voltage at the primary side, is something unknown, right. So then therefore we really cannot write these equations, here for this current IA, I capital V and I capital C, because the voltage at the neutral point is I unknown, right. So then therefore we have to do something such that this voltage at the neutral side gets eliminated, right. So that process makes this analysis more complicated, and also it basically makes it much more interesting. So we will do that calculation and do that analysis in the next lecture. Thank you.